Hello everyone, in today's video I'm going to be showing you all about two-dimensional LUTs. LUTs or LUTs or lookup tables are basically pre-computed data which makes your effects run faster, and you can basically use this data to do anything from color correction to automating expressions and a whole bunch of other things, but usually when dealing with Adobe we are talking of course about color correction LUTs. So in the context of today's video, 2D LUTs are going to be explained, but also through the lens of color correction. And you can think of a curves adjustment as basically a two-dimensional LUT, which has an input and an output, which can be changed. And a LUT is just basically like this, but it's pre-computed. This will all make sense later as I explain everything. And I'm going to be using this GitHub repository I created, which has some code and a whole bunch of descriptions to explain everything. Before we get started with this video, I do want to remind you down below, hit subscribe and the bell icon to be notified of new videos coming out twice weekly on the channel. And down in the description, you can check out the code for this in the GitHub link down below and follow along, or check it out for yourself. Make sure you follow us there for coding updates, and in the description, follow us on Instagram for other live updates. If you're not already a member of our Discord server, make sure you come and join to get help with scripting, extensions, plugins, expressions, submit tutorial ideas, and much more. And if you'd like to help support us on YouTube, you can become a member, supporter, premium supporter, or VIP, and this comes with cool perks like VIP streams, Discord status, and much more. And also make sure in the description you check out the AE scripts, Gumroad, and Adobe Exchange links for other tools and products I create. Alright, so let's just dive into this. Today's tutorial is going to be pretty detailed, and I'm going to be going over what a 2D LUT is, how we can sort of create our own, and how it relates to scripting and plugins. So what is a 2D LUT? A lookup table is a set of pre-computed data which can make your code faster. This basically means if you have a complex algorithm you need to run, instead of having to do it every single time the user refreshes a frame in After Effects or Premiere, for example, you could have them pre-calculated to, instead of having to do a complex algorithm which takes a lot of processing time, you could have all those values pre-computed, and you simply refer to an index in a list. A basic example of this is something like this, where we have a list of values going from 0 all the way up to 1. You can see I have 100,000 values here, and this could be equivalent to a LUT. Your input value could be something down here, and we're going to force the value to be whatever it is. So visually, this is a simple two-dimensional LUT in a file. Let's go on explaining more. Instead of calculating, like I said, a complex algorithm for every pixel, we can pre-compute the data and search for an index instead of the algorithms. So basically, to sum up, a LUT allows you to use an index search which has pre-computed algorithms baked into it, instead of having to do the algorithms every time, because if you have a more complicated algorithm, something as complicated as maybe even x squared, that's going to be saving you a lot of time if you're going over millions and millions of pixels. So just going to the index and getting that value is much quicker. Usually a LUT is organized in file rows or columns, and the depth and complexity of this is based on the type of LUT. There are 3D LUTs, and we'll discuss that later. When dealing with Adobe programs, we are usually referring to color correction or grading LUTs, which in one form or another are effects you apply or files you apply to clips. This can be a LUT or a cube file, or you could really name it whatever you want, as long as your program knows how to read it in. In the realm of these LUTs, which this tutorial is primarily about, there are 2D and 3D LUTs. A 2D LUT is one that has an input value, processed using an algorithm, into a single output value. A 3D LUT takes 3 input values, processes them into a single index, and processes them into 3 outputs. In the case of color correction, that's typically an RGB example. And I will be going over 3D LUTs in a future tutorial and show you how complex and powerful they are. But you basically are dealing with things in 3 dimensions and then creating different shapes to represent different color spaces, so you can convert this standard color space cube down into a color grade that matches some kind of filmic look or something else. So to look forward to that, make sure you subscribe, of course, and I will be making a very, very detailed tutorial coming up on that as well. So back to the curves adjustment. The curves adjustment is a sort of visual representation of a two-dimensional LUT. On the y-axis here, we have the input intensity of any given pixel from the low intensity up to the high intensity. So this is like a black pixel, and this up here would be if the pixel incoming was white. And the x is the output intensity for any given channel. So in this case, with y equals x squared is this graph. This is just a simple one short of a contrast curve, but we're just bringing down most of the lower mid values here. If our input pixel is black, the output pixel on the x-axis right here, which is represented by black pixels here, white pixels here, if our input is black, our output is also black. If we go up here to our most intense pixel, if our input is a white pixel, the output is not black, it is white. And same thing if we go over here to a middle pixel, this is like a nice gray pixel here, or if it's on a different color channel, it just has a 0.5 out of 1 or 127 out of 255 value. That is going to be outputted over here, which isn't quite, on the high end, but you can visually see basically this point here on the y-axis is black and white, and here on the x-axis is black and white. The input converted to the output. And then you can have multiple different algorithms which we bake into the LUT. So this is x squared. This is x cubed, which is a little bit more extreme of an exponential curve. And then you can also do things like square root of x, which is almost the inverted form of this. And we can calculate all these, pre-bake them into a LUT file, and instead of having to apply this complicated algorithm 1 million, 2 million times per image, we can have them pre-calculated. So the input pixel's intensity, let's say the RGB intensity or luma, is x. So basically you just have to plug it in, and y is going to be the output value. So in this case, if we have an input of 32 squared, sorry, I should say 32 pixels as our input intensity. Let's say that's 32 out of 255. We're going to square that in the case of x squared to conform it to this type of LUT or graph, and that gives us 32 times 32, which is 1024. This is far beyond the range of this 255 8 bits per channel color example, so what you can do is clamp it back between 0 and 255, or if you're using 32 bits per channel, you can have this as super brights. But because the input of this is 32 out of 255, that's quite a dark pixel, or has a low intensity of input, you could also say, then because it's going so high at such a low value, clamping will be really important because your low values are going to be already brightened too much. So if you're using 8 and 16 bits, it's pretty simple because your range is 0 to 255 and 0 to 32,768 for those pixel types respectively. But with 32 bits per channel, being 0 to 1.0 causes issues when doing squares and square roots. For example, let's say your input pixel value is 0.5. If you take 0.5 and multiply it by itself, or you square it, you get a smaller value of 0.25. So really, that's going to be the opposite of what you want. Instead of squaring your value, you're really, in this case, halving it. So this means that your input would be half instead of being squared. To get around this, when using 32-bit pixels, multiply them by 255 or 32,768 first before applying your calculations. Then after, divide it to commutate back to the original range. There's also no need to clamp in 32 bits like I said because you have overbright support. So in this example, if we go ahead and take 0.5 and multiply it by itself, like I said, if it's squared, it's going to be a smaller value. So what we want to do is take 0.5 and multiply it by, say, our 8 bits per channel range. That gives us the equivalent in that range of values. Then we can square that. So we just say squared. And that will give us a huge value of 16,256. But we also need to divide again by 255 to commutate back to the original range. In this case, we have 63 out of 1.0. So that's extremely bright. And you probably want to reduce that quite a bit. But it is possible to do it in all bits per channel. Just make sure you know that in float examples are a little bit different, and you may have to do a little bit of trickery to get it working properly. So all that math is what's actually being pre-computed and baked into our LUT file. That's so that we don't have to run those same operations millions and millions of times per image in the future when the user or us ourselves are using this algorithm or this type of color correction in this case. So instead, we will calculate what the output should be for every possible input, and we need to pre-decide how many different values we're going to use. I'll also realize there are some intermediary values that you can have interpolated, so you don't have to be extremely precise. You can get away with interpolation depending on how detailed the pixel data or whatever data you're dealing with needs to be. So for example, we could have a LUT file with 255 rows. each one containing a step from black to white, or the lowest to highest intensity. So R index 0 will be 0, R index 1 could be 0 as well, R index 2 could be 0.05, and basically, if our input luma was 0, we would know the output luma is 0. If our input luma was 1 out of 255, our output luma is also going to be 0. So we're doing a little bit of clamping there through whatever algorithm created this. If our input is 2 for luma, we could say 0.05, etc., and all the way up to the max of our color range we've decided. In this case, an 8 bits per channel color. We have 255 values, so the very last value here we could just say is equal to white or 1. You can use as many steps between the min and max of your chosen range you want, 0 to 255, 0 to 32768, or 0 to 1.0. And once again, 32 bits per channel is a little bit different. With 8 and 16 bits, they're integers, so the max number you can kind of use is the max number of steps that is defined by this number here, 255 or 32,768. But with 1.0 being a float, the number of steps is really up to you. You could have an infinite number of steps between it in reality. Whatever number you'd like to call this, you could have that many steps between 0 and 1.0 because you simply just have to add more decimals. But there is a certain level of detail that are beyond the limitations of color precision of After Effects, computers, monitors, and your eyes. So the majority of 3D LUTs that I've seen actually that are for color correction are 64 cubed, meaning that there are 262,144 steps between the min and the max of the provided outputs. That means when a 32 bits per channel or a 64 cubed LUT file is created, it's analyzing an image between black and white and creating 64 cubed steps between it. In the case of a 3D LUT, it's because you have an R, G, and a B channel, so you have 3 axes on a hypothetical color cube, and that turns into 262,144 steps to interpolate all the possible values between black and white. Just as a visual example, here are what the number of steps will give you in terms of a decimal. If you want 100 steps between black and white, each step needs to be 0.01. If you want 1,000 steps between black and white, or again, these are interchangeable terms, black and white, low intensity, high intensity. It's really an input signal. If this was a piece of analog equipment, the signal would have like an input voltage or electricity or intensity, and that could be represented as a sound, that could be represented as a light, could be basically an input intensity. In this case, we're mostly referring to black and white. It could also be a red channel intensity, green channel intensity, blue channel intensity, and a whole bunch of other values. It's really arbitrary. But anyway, 10,000 steps between the lowest and highest intensity with 0.001, etc., etc., etc. You can get pretty detailed, but again, there is a certain point of diminishing returns where you will not notice any difference. Alright, so now let's discuss some code. How do we create a 2D LUT? Creating a 2D LUT file is pretty straightforward and is a pretty fun exercise of automation. It's simple enough that we can actually do it in a script if we want to. As you know, sometimes scripts can get a little bit bogged down when doing millions of operations, but in this case, if we just do, say, 100,000 steps, it's not too bad. So one cool thing is that with LUTs formatted in this way, is that the input value is implied through the row of the new LUT file. The first row in our LUT is the minimum inputs result. In the case of color correction, a black input, 0 for red, 0 for green, and 0 for blue. The last row in our LUT file is our max input result, or white, and the number of rows is our number of steps. So if we have 1,000 steps inside of our LUT file, or inside of our LUT analysis, we're going to have 1,000 rows in our LUT file itself. So there's some implicit information inside of your LUT file, which will make things a little bit easier. So now let's look at how we can write this LUT file. So in this case, we're starting off by creating a LUT file in our documents, and we've defined the number of steps. We're going to analyze it as 100,000. Then we're simply going to create an array called LUT data. Each one of the indices of this array is going to have our data here. We're going to have an input value, and then we're going to output it here. And basically the input again is implied through the row, and the output is whatever value we define here. So if we want to do it very simply, you could use this algorithm to create whatever kind of LUT you want. in this case, we have a for loop which loops through the number of steps, and each time we're going to push something into our LUT data array. And what we're going to push into it is the result of a function called equation. The input of the equation is going to take an index, and the output is going to be what is our LUT data. In this case, you can see we have equation defined with an input, and in this case, the input is always going to be our index. So the first time it goes through, the index is 0, next time 1, all the way up to 100,000 steps. Then what we can do is define whatever we want to be our equation. In this case, what I'm doing is I'm basically running a square root operation on our input. And I'm also going to have a clamp operation which says if my value is higher than 255, return 255. If it's lower than 0, return 0, just to make sure that my input or my output of this square root function is also being clamped appropriately. And the output of our LUT file will look approximately like this. One other thing I didn't mention is we're also dividing by 255 to get the float equivalent. If you just kept it like this, you would have integers in here. But if you want your data to be float, which sometimes is better to have because you can easily interpolate that and it can have more detail than say a value of 1 and 2. There's only an integer between that rather than all these decimals. Then lastly, we're simply going to write all that LUT data we pushed into our LUT data and join it so it lines up nice and vertically. Like I said, it's gonna produce this file, and you can then use this data to do whatever you want. This could be representative of a pixel data. This could be representative of honestly pretty much anything that can have a value that ranges. Anything that's binary, like a checkbox, wouldn't be able to work with this. But even a slider value, if you input the slider value and the slider value is 52, then it could clamp it to this value. So anything that can have a value that ranges can have LUT data applied to it. So now we've pre-computed the square root of the input 100,000 times, and you can run the script yourself and get this data outputted. This may not seem like a lot of time saved, but if you are doing large amounts of iterations or a much more complex algorithm, which is common in higher order like 3-dimensional LUTs, the time saved can be significant. And especially if you're dealing with large pieces of footage, again, 1080p is like 2.7 million pixels or something like that per every frame. Having to do a complicated calculation is too much processing. All right, so now the next fun part is reading our LUT file. So lastly, we need to be able to read all that data we exported back in. Let's say at this point you've automated the creation of 100 2D LUT files and you want to be able to read them back into After Effects somehow. This is where it could get fun, and the possibilities for a 2D LUT are seemingly limitless, as I mentioned. The input could be anything, a slider value, a pixel's luminance, pixel's red intensity, anything that has a single dimensional value, and I should caveat, and can have a range, and is not like binary or trinary, tertiary. For the purposes of this, let's assume our LUT is to adjust the look of an image, and we're going to apply the single dimensional output for any given input to the R, G, and B channels to apply our LUT. Let's basically we're going to apply the LUT output values to our red, green, and blue channels, which will give us the look of either darkening or brightening of the image because we're increasing or decreasing the intensity of all of our color channels. So let's do this with a plugin. And remember, the row number of our LUT file is the input value. If we have a 32 bits per channel pixel and we calculate the red channel intensity as 0.5 or 50%, there is no row 0.5. So we sometimes will need to interpolate the value of our pixel range, our pixel input range, to our LUT range. Basically, we need to take the 32 bits per channel pixel range and stretch that up to be the range of our LUT file. We know the LUT file range is the number of rows we have, so you just need to basically multiply, in this case, by that number. The nice thing about 32 bits per channel is 0.5 is easily a scale, and we can multiply that by any number to get its range. For example, 0.5 of 100, multiply them together, and you get the equivalent range of 50 out of 100 instead of 0.5 out of 1.0. So all you have to do to get the interpolation of the range, you take the input divided by the input range max times your row number. So in this case, we have maybe our input is 0.5, like I said. The input range max is 1.0, which just gives you 0.5, times our number of rows. Then we can floor that value to get the integer In this case, row 5000 is the same as saying a 0.5 intensity pixel in 32 bits per channel. So if we create an array that holds each row of our LUT file in each of its indices, we can apply our LUT with basically one line of code per channel. So for example, in this code here, we have a nice mix of JS, C++ pseudocode I made. We have a LUT file, for example. Let's say this is the one we just exported. You could reference whatever file you want. We're going to create a LUT array. We know we have 100,000 steps, so let's store all those values in there. And this is going to be equivalent to our LUT file. We're going to read it and split all the data based on their different rows. So we're going to split based on /r/n, depending on what language you're using. And this will return our array of 100,000 LUT data points. Then really all we have to do is use this above interpolation algorithm. We're going to set the output red, the output green, the output blue, all equal to their respective LUT values. To do this, we're going to take our entire LUT array, which again has 100,000 points in it, and we're going to get what index? Well, the index we get needs to be, again, based on our input value, interpolated to our LUT range. In this case, what we're going to say, well, we need an integer because this is an array index. We're going to floor some kind of calculation. The calculation we're going to floor, or make into basically an integer, round down, is to say our input red value divided by the max possible red value, 1.0, times the range of our LUT, or the number of numbers in our LUT. I do realize this is 10,000, not 100,000. This should be the number in your LUT, the number of rows. So we're basically taking the input, calculating the intensity out of values that we can use as a multiplier, and we're going to multiply it by our number of steps in our LUT. We're going to do this for all channels. Take the input green, multiply it, and get the proper index. Take the input blue, get the multiplier, multiply it by the number of rows in our LUT file. And this will set the output values appropriately for each channel. More explicitly to say, if it detects that the input pixel of that you're applying the LUT to is pure white, or it's 1.0 out of 1.0 intensity on the red channel, it knows to go check this very last value, because we're taking 1 divided by 1 equals 1 times 100,000, and that gives you row 100,000. So that means with that intensity of that pixel coming in, this is the output value we need. And that's going to be applied for all your pixels, no matter what the intensity. It's basically going to convert the channel or pixel intensity you give it to a row, and in your cube file or your LUT file, this is then going to give you an easy output value, which you can simply apply to your output red, output green, output blue, or any other channels. So like I said, this does apply the same two-dimensional LUT to all three of your color channels, but there are many variations and fun things we can do. Using different equations for different channels is essentially like using a curves effect and changing various individual channels. If you remember, our curves effect is a great reference to how LUTs work, at least these two-dimensional LUTs. This might be, say, like an x squared value, but if you remember, we had that square root value, which looked more like this. So you can apply LUTs to different channels using different equations, and this will give you different looks overall. Because after all, when I move these curves around, I'm really just creating a mathematical equation with points here. And there is one additional level of detail we can add. In this case, we're flooring our input value to make sure that we have a valid integer for our LUT array so that we can refer to an actual row or index of an array. But if we're flooring it, we are forcing it to be a value less precise than it should be. If our index should be, I don't know, 5000.1, it's not going to be the same value as 5000 or 5001 or 5002. We got to interpolate between them. So, like I said, we have an example here. Our input row could be 5000 point blah blah blah, and although this isn't a valid row, 5000 and 5001 isn't technically accurate for how this result should be. So we should interpolate between those two rows' values. So it's pretty much the same as previous. We're reading in a LUT file, and we're getting all the data and storing it into an array. And we're basically going to have two cases. If we find that when we floor our LUT file calculation to get the row of it here, we take our input divided by its max times the number of rows. If we find that flooring it gives us the same value as not flooring it, that means it's already a valid integer. So what we're going to say, if it's not the same, if when we floor our calculation is different than when we don't floor it, that means it needs to be interpolated. To interpolate it, we're simply going to set the channel equal to our same calculation as before. We're going to reference our LUT array and floor our input channel value times the number of rows, and then we're going to add that to the next index. So we have our main index, and then we're going to add +1, divide them by 2. So you can then basically simply average them and interpolate them. Otherwise, if we know it's an integer, just run the normal calculation. If we know that it's not a perfect integer, not that we have to interpolate it basically, again, just add the current index and the next index of the LUT array, divide them by 2. All this above is experimental code that I kind of just wrote as an example. Obviously, a lot of the numbers are wrong, but I do have actual plugin code attached that you can check out, which is running all the same stuff to create these results. So you can check out the code in this repository and install the plugin, build it, and apply it by going to Effect, NT Productions 2-dimensional LUT. And in this case, well, of course, depending on your LUT file, it is hard-coded to have a LUT file in your documents folder, which you can change in the code. But in this case, we have basically like an x squared or an x cubed. I believe this is an x cubed change in the image. And this is what happens when we apply all that we've learned today to our LUT. We basically have our input pixels, and in the case of an exponential increase, are going to, for the most part, the darker pixels will remain close to the same, but as you get to the low mids, and especially the highs, it's going to start peaking out around the max intensity, as is part of LUTs and exponentials. And I think that's going to do it for today's video. I think I've done a decent job at explaining LUTs, 2-dimensional LUTs, specifically how you can apply them practically using color correction. And again, all these concepts can be applied to anything. It could be slider values, values of other effects. It can literally be linked to anything that can have a changing range of values. So if you have any questions, of course, leave them down below. I will link to this repository so you have this full descriptive guide on all this LUT information. You can also check out the plugin source and all the example code and images used in here, all free to use and try out for yourself. If you enjoyed the video, hit the thumbs up button down below, hit subscribe and the bell icon to be notified of new videos coming out twice weekly on the channel. And down in the description, you can check out the code for this in the GitHub link. Follow us there for coding updates, and in the description, follow us on Instagram for other live updates. If you're not already a member of the Discord server, make sure you come and join to get help with scripting, extensions, plugins, expressions, submit tutorial ideas, and much more. And if you'd like to help support us on YouTube, you can do so in the description by becoming a member, supporter, premium supporter, or VIP, which comes with cool perks like VIP streams, membership status on Discord, and much more. And also in the description, make sure you check out the links to my AE scripts, Gumroad, as well as Adobe Exchange for other tools and products I release. Thanks again for watching. We'll see you next time.